Okay, good afternoon, everyone. I'm Xueke from the University of Science and Technology of China. Today, I will discuss a free-induction-decay scalar magnetometer for precision measurement. This work is done with my lab mates Zhang He, Tong Gong, and my advisor, Professor Dong Shen. As the performance of atomic magnetometer continues to improve, we are expected it to useful in many fields, such as geomagnetic field detection and fundamental physics applications. These applications require a high-sensitive and accurate atomic magnetometer for non-zero field detection. So the scalar magnetometers extract atomic precision frequencies and roughly in three different ways by the radio frequency fire driven type or optical driven type and FID type. The first two of this type are operate in a closed loop mode, and this mode can take systematic errors such as phase error in the feedback loop and the light shift from the pump beam. But however, the FID type can avoid this systematic error. But the FID magnetometer require a very different hardware for operating. So in this work, we are focused on a free induction decay scalar magnetometer. The operating principle of the FID magnetometer is illustrated in this plot. During the pump stage, the intensity of the pumping are modulated for Bell-Bloom optical pumping. During the probe detection stage, we close off the pump beam, and the probe beam can record the polarization of FID signal. Each cycle in our experiment, each cycle of measurement lasts 8 million seconds, and with 3 million seconds for pump and 5 million seconds for probe. And by performing a real-time data analysis in the signal, we can extract the magnitude of the magnetic field. To enhance the signal-to-noise ratio, we use the multipass cavity in this cell, and the number of reflections is 26 reflections. And we filled the cell with rubidium 87 atoms and nitrogen gas. We operate the cell at a temperature of around 85 degrees Celsius. And this is the design of the scalar magnetometer. The sensor head is a 3D printed platform, and the pumping and probing are coupled into the sensor head by an optical fiber, and the polarization of the probe beam after transmitting from the vapor cell is detection by the polarimeter, and the electronic signals are sent out via multiple coaxial cables. This is a picture of our sensor head. To operate the FID magnetometers, we also the electronics are also homemade, which include controls of lasers, cell temperature, time sequence, and real-time data analysis. The control of time sequence aims to produce a frequency adjustable and the duty cycle adjustable square wave to drive the AOM for pump beam. we generate a square wave by comparing the sign from the DDS and the reference voltage to, and then if we adjust the reference voltage, the duty cycle of the square wave are adjustable. And the data analysis electronics aims to extract the frequency of the FID signal. To realize this data process, we use a Hilbert transform in the ARM core. Firstly, we use a Hilbert transform on the signal. It can shift the signal by 19 degrees, and then we calculate the instantaneous phase of the signal. Then to accumulating the instantaneous phase, we can get a curve like showed in this figure, and the slope of this figure is the angular frequency of the FID signal. Firstly, we operate the FID magnetometer in an open loop, and this is the performance of the magnetometer. The performance of two separate magnetometer showed in this figure, and we used a gradometer to cancel the common noise of the magnetometer, and from this figure we can see the performance of the magnetometer below 1.00 Tesla in 1 second, and better than 1 Tesla for an integrating time of 1,000 seconds. Compared to the state-of-art scalar magnetometers for EDM experiments, our system shows a better sensitivity in a short time, and comparable stability in the long time. So we plan to use this magnetometer in U-turbine EDM experiments. But there is a problem in the open loop mode. The fluctuation and the fluctuation of the magnetometer are unavoidable. So in this plot, we apply a modulation magnetic field of 2,600 nanotesla per second into the system, and this so large magnetometer beyond the bandwidth of the open loop mode magnetometer, so we can see a sharp decrease in the signal. So for keeping the sensitivity of the sensor, we need a real-time closed-loop control for the system. In the closed-loop operate mode, we use the frequency of the FID signal from in the previous cycle, send this to the controls of time cycle as the modulation frequency as the for the pumping in the next cycle, so we can implement the closed loop control. This is this plot shows we apply a magnetic modulation field with different rate into the system, and we test the response of the system. As we can see in this figure, with the increase of the slew rate, the difference between the frequency of FID in in previous cycle and the resonance frequency in current cycle increase also. So we can see the signal, the sensor signal are decrease with a slow rate. In our system, when we implement a closed loop, if we apply a magnitude modulation field of 2,1600 nanotesla per second into our field, as we can see the signal of our sensors reduced to 17% in the initial signal. And in summary, we have developed a highly sensitive and stable FID scalar magnetometers, and we will apply them in precision measurements. And using the homemade electronics, we also successfully implemented closed-loop control for the magnetometer, achieving a typical resonance rate of 2,600 nanotesla per second. Thank you for listening.